Hey everyone, today's lecture is Chapter 10, Precipitation and Agglutination Reactions. And again, it's from Chapter 10 of your textbook, Clinical Immunology and Serology, a Laboratory Perspective, 4th edition. So let's get started. Immunoassays are tests that have been developed to detect antigens or antibodies in the serum. Many are based on the principles that we're going to review today, called precipitation or agglutination. In a nutshell, agglutination testing involves antigens like cells, like those on cells, the things we've been talking about, but antigens such as cells that when they combine with antibodies, they form an aggregation or almost like a clumping to form larger complexes that are going to be visible to the naked eye. We see them in, for example, red blood cell typing in blood banking. I know you've done that. That's an agglutination reaction. Precipitation reactions, on the other hand, involve combining soluble antigen, which we know that means dissolved, right? Soluble antigen and soluble antibody that when they combine, they eventually produce an insoluble complex, which then we'll be able to visualize in the laboratory. So the chapter overview, we're going to look first at antigen-antibody binding and some of the properties of that, precipitation reactions, some of the agglutination reactions, some instrumentation and quality control. Some of the key words that we're looking at today. Precipitation, as I said, involves combining soluble antigen with soluble antibody to create insoluble visible complexes. So by themselves, you can't visibly see the antigen, you can't visibly see the antibody, but when we combine them and we get antigen or antibody binding to antigen, we're going to be able to create visible complexes. Agglutination, on the other hand, is that insoluble antigen, things like cells, other things that we're going to see, that are going to aggregate to form larger complexes when the antibody is there and is present. We're going to talk about multivalent antigens, and when we're talking about that, we're talking about antigen molecules that, are antigens are foreign things, with more than one identical isotope, or epitope, more than one identical epitope per molecule. So remember we talked about that antigens don't have to be the same on the antigen binding sites don't have to be the same on a pathogen. They can be varied. We can have different epitopes. But in this case, when we're talking about multivalent antigens, we're talking about more than one identical epitope on the molecule. And so we call that valency. We talk about the binding capacity. So multivalency is more than one valent or more than one combining site. We frequently see this as repeated epitopes, multiple versions of the same epitope. And so when we hear these terms, multivalent and polyvalent mean the same thing. There's more than one identical epitope on an antigen. And again, valency is just the combining site. So one valent is one combining site. Multivalent means multiple binding sites. And that's going to be important because that's how some of these reactions become visible in the laboratories, by having antibody be able to be binding to multiple sites across antigens. And if multivalent antigens are multiple binding sites, then what do you think multivalent antibodies? The multivalent antibody is saying that we have at least 2 antigen binding sites. So an IgG, if we think about IgG with our Y shape, we had an antigen binding site here and an antigen binding site here. So IgG has a valency of 2. There are 2 antigen binding sites on an IgG. An IgM pentamer has 5 identical Y shapes, each with a valency of 2. So if we have five monomers combined with J chains times times a valency of 2 each, we have 10 antibody binding sites per IgM molecule, per IgM pentamer. So if we have a dimer of IgA, what would be the valency of IgA dimers? I'd like you to write that on a piece of paper. We're going to pass that in, or you're going to actually send that to me in an email, probably an email. I might make it a discussion post. But you're going to answer some questions during today's lecture. I have some homework questions within the lecture. They're numbered 1 through 5, but I want you to have sort of a pre-1. This is question 0. So if IgA, a dimer of IgA has a valency of how many? Question mark. You need to tell me that answer. Yep, so we're going to move forward here. There we go. Good. The principles of agglutination and precipitation reactions are based on, again, the simple binding of antibody at the FAB site. So we know that this is the antigen binding site, right? We've talked about that. And we're going to bind this site, this specific site of an antigen, an antigen binding site to the antigen. So the epitope on this pathogen or this antigen. We know that not every antibody fits every epitope, right? So we can have different antibodies. I wish they had done them in different colors or in some way made them look respectively different. But this is supposed to reflect that there are multiple antibodies that have different antigen binding sites. And we need that because we need to remember that this pathogen, whatever it may be, is not going to have just all the same epitope. We've talked about that. And that the antibody-antigen reaction is going to be, its efficiency and its success of binding to the epitope is going to be based on a couple of concepts. And that is that of affinity and avidity. Affinity and avidity are talking about the reaction between antigen and antibody. We're going to look at these in just a second. But both of these concepts are required to make a good antigen-antibody binding. So let's look at affinity and avidity in detail. We're also going to, in a moment, look at the law of mass action. So let's look at affinity first. Affinity is referring to us the initial attraction between a single FAB site on an antibody and a single epitope or determinant site on an antigen. So we have an antibody that has a receptor, an antigen binding site that matches exactly the antigen itself on the pathogen. We know this. We know that the better the affinity, the better the fit, the stronger the attraction. So the strength of the attraction, the strength of the affinity, depends on how specific this antibody is to this antigen. So we can see we have antibody 1, and it's only binding to epitope 1. Antibody 3 is specific to epitope 3. Antibody 1 is not going to bind to antibody 2. Look at the structure. Imagine those are amino acid sequences. They're different, right? So antibody 1 can't bind to epitope 2. They're different structures. So affinity is just, again, referring to the initial attraction between the epitope on the antigen and a single FAB site on the antibody. And that's the matching antibody to that epitope. Avidity, on the other hand, is going to be defined as a measure of the overall strength of the antigen-antibody binding complex that we just saw. It's a combined strength of all the forces that keep an antigen and antibody together once they've combined. So affinity is that initial binding. It's that initial attraction between antigen and its specific antibody. Avidity is what keeps them together. It's the strength of the antigen-antibody binding that keeps them together. Does that make sense? Affinity is the initial attraction. Avidity is the strength that keeps them together. In the host, as a specific antibody comes in close proximity to an antigen or an epitope, there are different kinds of bonds that are going to hold them together. These include ionic bonds, hydrogen bonds, hydrophobic, and van der Waals forces. If we think about it, and we can remember from chemistry, we remember that ionic bonds are held together by oppositely charged particles, while hydrogen bonds are quote-unquote polar bonds, referring to the attraction of kind of positive and negative charges that reside on the hydrogen molecule. It's that positive and negative attraction that, just like magnets, holds the bonds together. Hydrophobic bonds, on the other hand, hold together less because it's a real bond, but really more in the fact that the molecule is hydrophobic. It doesn't like the water around it. So it's sort of like better to be bound to something you don't want to be bound to than to be bound to something worse for you, which would be water. So instead, the molecules hold together because the alternative would be to bind to water, and it's not interested. It turns away from it. It turns inward, and it causes a binding that sticks together. And then really quickly, van der Waals forces are not so much bonds, but just a means of attraction between neutral molecules. All of these bonds are relatively weak. And because they're weak, the binding using these bonding, that initial attraction, that affinity, is reversible. So you can have this initial binding between antigen and antibody that can be good affinity, initial attraction, but the bonds that hold it together are really weak. And so that makes that initial antigen-antibody binding reversible, means it can be undone. As we can remember, the strength of the attraction between antigen and antibody is going to depend on the specificity of the antibody for that antigen. We remember the concept of lock and key, that if it's a good lock and key, that if a specific antibody was created for a specific antigen and they come in contact, that's a really nice lock and key fit, and so we have a strong attraction. So affinity, what did we pull from this? The bonds that hold the initial antigen-antibody binding together are very weak, so they're reversible. And that the strength of that attraction, that long-term strength of the attraction, is going to depend on how specific the antigen-antibody reaction is, much less than the original bonds that hold it together. Let's look at an illustration of affinity. Looking at this slide, we can see that in this illustration, the same antibody and antibody can bind to multiple epitopes or determinants of the antigen. So if we look at this and we assume this is the antibody and here's our antigen, they're similar, but they're not identical. Clearly they're not identical. They're similar in nature, but not identical. If we look closely at this illustration, I believe it's on page 141 of your book, we can see the binding on the left is stronger, has a stronger bond to the antigen and a better fit between the antigen and antibody. So it is going to be a higher affinity. That initial attraction is going to be better. In other words, the initial attraction is stronger, so it's more likely to hold. We can see that we have, this is a polar bond, a positive-positive bond, positive-negative bond. And this is a positive-negative-positive bond, which would be lovely, but this is a negative-negative-negative bond. This is not going to be a happy bond, so this is a lower affinity. The initial strength is not going to be terrific. So a good antibody that has a good fit in between is going to do well compared to one that doesn't really fit in the antibody binding site. When we talk about that lock and key analogy we've been talking about in prior lectures, we're still talking about affinity. Affinity, the strength of the antibody-antigen reaction, is going to be dependent on the fit of the elements. So if we have got that initial attraction, remember we have them bond with those weak kind of either ionic or hydrogen or van der Waals forces, whatever it is that's holding it in place. But we said that that's a reversible bond. They're not a strong bond. However, if we have great lock and key fit, it's going to help make our bond stronger. We're not going to rely on those really weak initial forces to help us keep it bound together. So this picture is demonstrating again. I prefer this picture to this illustration to this one, just because I think it really illustrates a good fit. This is clearly a antibody that binds strongly to an antigen because it's a great fit. So if you look here, you can see that the binding sites are matching up perfectly. You know, structurally it's right. This antibody is made to respond directly to this. This is a similar epitope. And so it binds slightly to the antibody. You can see there's some binding here, but they're not a great fit, and structurally it's not a great fit. So this has a lower affinity. The bond is weaker, and so because these bonds are weaker, they dissociate. They can break apart. So that's what we mean when we say that this is a reversible reaction. Low affinity is a sign of, we can see this, for example, in a cross-reacting kind of a binding. That cowpox, smallpox thing that we've been talking about would be an example of something where it might be close enough that the antibody does a little bit of help for you, but it's not a really tight bond. It's not going to stay stuck together, and it's not going to be a perfect bond. So this is going to dissociate. It may provide some protective immunity for the person, but it's not a long-term solution. High affinity means a great lock and key fit, and these are going to stick together very well. Low affinity are going to be the ones that dissociate, and we're not going to be able to count on those initial attractions, those hydrogen bonds, to keep it together. It's just not a strong enough fit for us to count on those weak bonds to keep us together. So that's affinity, the initial attraction and the strength of the reaction based on the fit of the elements involved. Avidity, on the other hand, is the sum of all of those forces, the combined strength of all of the forces that hold multiple antigens and antibodies together, holds the molecules together. So it's not just those binding forces that we talked about. It's not just the bonding and whether the ionic or covalent or whatever it is, van der Waals forces hold it together because it's a great fit. It's not really about that when we're talking about avidity. We're talking about multiple antigen-antibody bonds, and that is what contributes to the long-term strength of holding these molecules together. So we alluded to the fact that we had valency issues. IgG, as we said, had a valency of 2. Here's an IgG molecule. Here's one binding site, here's another binding site. Valency of 2. IgA, it's a dimer, has 1, 2, 3, 4, 5, 6. Oh no, 1, 2, 1, 2, 3, 4. Has a valency of 4, and IgM has a valency of 10. 2 per monomer that are held together by a J chain. So 2, 4, 6, 8, 10. That has a valency of 10. Clearly, IgG and IgD also have a valency of 2. So we talked about just a moment ago that affinity, that initial antigen-antibody bond is easily broken because it's a really weak bonding system. But avidity can help us overcome that weak initial bond. It's because we're going to bind multiple epitopes at the same time. So I don't want to say, can't think of the word that I want to use. The idea that the reaction, the bonding is not going to hold, the sort of intent that those are weak bonds are overcome just by sheer strength and sheer force of the number of bonds that we have. So that if you can imagine, we have antigens on several different pathogens, or on the same pathogen itself, actually, and we bind multiple antibody determinant sites with epitopes, matching epitopes on the antigen. That's going to help keep it on stronger. So it's sort of like, imagine yourself you're over the edge of a building and someone's holding on to you with one hand and you feel yourself kind of slipping. But if they grab you with two hands, you got a good chance that they're going to hold on to you tight. Now imagine that there are, 4 other people up there and they're all trying to hold you up from falling over the edge of the building too. It's a strength. It's individually each of those bonds are weak, but as a group, they're much stronger. That concept of group strength, I call it kind of brute force, is avidity. Avidity is less likely then to reverse because, again, we have many, many binding sites that are that we have an antigen-antibody binding. Avidity, as I said, is influenced by both the valence of the antibody and the valence of the antigen, which is why it's important that we have those multivalent antigens and multivalent antibodies. Avidity, by definition, again, is just the measure of the overall strength of the binding, which influences the stability of an antigen-antibody binding complex. So let's look. This is sort of the example I just gave you. So if we had something with a low, this is an affinity, right? So this is that initial binding. Here's our antibody out scouring the town looking for its matching antigenic epitope. Its antigen to bind to. Finds it, we get one little binding to an epitope, and remember we have little weak bonds here. This guy's hanging off the edge of a building. This weak bond is not going to hold him together. But we have 2 weak bonds, but now we've got 2 epitopes being bound. By sheer force, we have a higher likelihood of being able to maintain those bonds, just because even if one of the quote-unquote hands lets go, the other one's still holding on. You have time to grab it back up. Then this one lets go. The idea that they're both going to let go at once is low. So avidity is stronger. And this we're going to see, this is going to talk about the strength of that bond. Now imagine you have 5, you have 10 hands, 5 pairs of hands, and they're all binding to antigen binding sites. That increases the strength of your bonds and your ability to maintain that bond very strongly. So the more binding power we have because of valency, the higher our avidity. So if valency strengthens the antibody binding to the antigen, we know that something with a low valency needs to have, a low valency, a valency of 2, needs to have some way to keep it together, in which case this reaction, this antigen-antibody binding will stay together in a case of low valency if there's a really good lock and key fit. This one, if it looks like this, that high affinity that's going to help us keep those kind of weak bonds together and strengthen them because they're so tight in a lock and key fit. So it doesn't matter that you have a low valency if you have a strong affinity. Similarly, a high valency, like with IgM, can overcome or compensate for a less great affinity. What does that mean to us? If we're looking back and thinking back about our primary immune response that we talked about a couple of weeks ago, we have that primary immune response. And do you remember what the first reaction is? What is the first antibody that responds? It's IgM. Is IgM created specifically for that antigen? Is it a great pairing? It's not. It's a weak bond. But the fact that we have a valency of 10 for each IgM molecule helps us to compensate. And so that's how we get that initial immune response, even though we don't have great antibodies being created yet. Over time, we start to develop those IgGs. And the IgGs, if we remember, are much more specific for the antigen. So the fact that we have a valency of only 2, the fact that we have a better lock and key helps us to maintain the antigen-antibody binding in spite of the fact that we have a valency of only 2. So you have to have one or the other. Either if you have a low valency, you need a strong affinity. So if you have that low avidity, you need a high affinity. In reverse, if we have a low affinity or a low specificity, a bad lock and key, we can overcome for it just by the brute force of having high valency, a lot of stuff sticking together. This, you'll be helped to remember this if you can remember what valency means and which molecules have what kind of valency. So remember, in this illustration, IgG has a valency of 2. So if it has a low valency, we have to have a really good specific antibody. IgM, which is created first, has not a great lock and key, but there's tons of valency. Brute force is going to help us keep those antigens and antibodies bound together. And then, of course, in the secondary immune response, it's primarily IgG because by then we have super specific antibodies being created. The concept of antigen-antibody binding, I told you before that that's reversible. And there's an inherent equilibrium that is in play here, and that is that the concentration of antibodies and antigens in the serum are equivalent at any time to the amount of antibody and antigen that are bound together. This is the equilibrium that governs the rules about antigen-antibody binding, and we call this rule the law of mass action. However, even though the antibodies and antigen binding is governed by laws of mass action, we're reminded that we need to factor in the strength of the action as well. We need to factor in what the likelihood of reversal is, not just how much of these free and bound reactants are there. The strength of the bonding is important in the laboratory, and we're going to need to assume some ideas about the laws of mass action when we're starting to create lab testing and interpreting lab results. So let's see this concept of equilibrium and strength of the reaction played out by using the calculation that's associated with the law of mass action. So we're looking at the the constant K, or the value of K, is referring to the concentration of bound antigen antibody. So this is a complex. Antibody is bound onto its antigen, divided by the amount of free antibody in the serum and the amount of free antigen in the serum. I know this is tough to look at, and you're like, I'm not really sure yet. Let's look at two simple examples I have here. So that when we calculate the calculation of K, that constant that's going to help us determine how strong a reaction is, let's look at some simple examples, and we're going to see what it means to have a high or a low value of K. That's going to dictate for us whether or not the antigen antibody complex is strong enough. So let's look. If we're putting in our factors into our calculation. So if we have 100 units of bound antigen and antibody, that means they're stuck together. The antibody has found the antigen and they're bound together. And we have 20 units of free antigen and free antibody. We divide 100 by 20 and we get a K of 5. So in this case, we have far more complex antigen antibody than free. And so as a result, we're going to expect that the K is higher, so it means there's more bound antigen antibody complex than free. And so there's a less likelihood that this is going to dissociate. We've overcome this reaction. If we have just a few, 20 units of complex antigen antibody and divide it by a lot of free antigen antibody, we get a K of just 2. And the value of K then, the law of the mass action, how reversible this is, depends on the strength of the binding. So these high values of K, this K of 5, is telling us that there's more antigen antibody binding complex, and we're actually going to be able to see this reaction more visibly in the lab. Simply put, if the K is higher, it means there's more bound antigen antibody complex than free. And if the K is low, it means there's less bound complex of antigen antibody than free. So if we just do this simple math, we're going to be able to see the reactions between the two, and we're able to assess. So if there's a K, is this reversing or is it not? It's not. This is staying stuck. This is staying stuck together rather than free. So this is a very strong reaction. This is a very weak reaction because clearly much more of the reactants are remaining free in the serum. So this is telling us a lot about the strength of the reaction, the laws of mass action, and how strong that antigen antibody binding is. It's not going to be reversible under every circumstance. Remember, we can overcome this reversal by either having a great affinity with a great lock and key or a lot of valency. So those two things are going to make you lean more towards complex than free. The tendency is to always, like everything in the human body, is always to go to normalcy. It's to go to equivalency, between in and out. So if we had the choice, which is preferable to use in lab testing? Tests with, I should have put this in here. Let me just do this. Which would you choose? A test with, A, high affinity and low avidity. B, high affinity and high avidity. C, low affinity, whoops, I can't type, affinity and low avidity, or D, low affinity and high, oh, look at me, I'm a great typist, high avidity. Which would be preferential? Clearly, it's something with high affinity and high avidity. We get a great initial attraction in the lab, and we also get a great strength of the binding that's going to stay stuck together. Why in the lab do we want things to be stuck together? Well, we're doing testing and we want to be able to visualize this, and we need to be able to keep things stuck together in order to have enough time to see the reactions come to play. So, what kinds of factors are going to influence the antibody-antigen reactions in the laboratory? There are a number of factors that we see that influence the reactions that take place in the lab. Remember, we were just talking about in vivo or in the body, but in the lab things might be a little bit different. The relative concentration of reactants, that is antibody to antigen, that's going to have a play, that's going to make a factor. We're going to see in a few minutes why. Temperature is going to influence the reaction. Length of incubation, how long we stick antigen and antibody together in a test tube before we look for a result. The pH of the test can also influence the antigen-antibody reaction. So we're going to focus primarily on the concentration of antigen and antibody in the test first. But for a minute, we need to just look at a couple of the phases of antigen-antibody reactions before we start talking about anything beyond simple binding. So when antigens and antibodies get together and they have that initial reaction, there are three distinct phases of antigen-antibody binding. The first is called sensitization. All this is saying is that antibody binds to antigen. If you see we have one antibody bound to one epitope, that's sensitization. It's just covering an antigenic site with an antibody. Sensitization. Sensitization is not a visible reaction in the lab test ever. There's no way to visualize this. We can't see antibodies, and there's not anything we can do to visualize this. We don't see a visual reaction, even though in the lab this has taken place. We don't know it yet, though. So the secondary phase of antibody-antigen reactions is called lattice formation. And what happens here is we see one antibody binds to an epitope on one cell, and the other arm of the antibody binds to an epitope on another cell. This is very two-dimensional, but if you remember, we talked about the hinge that's here, and how these can actually, it can make this arm reach way behind, and it can bind to an antigen way back here or over here. We can make conformational changes of the antibody 3D structure to do it. But for visual purposes, we see one antigen binding site to one epitope, and then it binds to another. Now we have many antibodies binding to many epitopes on many cells or many larger components. Could be a cell, it could be a particle, could be a bacteria, it could be many things. But the fact that we now have multiple either pathogens or cells binding with antibody in between them, they stick together, and now we have a pretty large formation. Here we have the same thing, one antibody, one antigen, but they were by themselves. Now we're forming them together. It's going to form a large complex that's suddenly visible in the laboratory. So lattice formation is a visible reaction in the laboratory. This we're going to term an agglutination. So, and you can see here, agglutinates out. This is what happens when we're doing blood banking. This is one of the ways that we see it. And tertiary reactions, we're not going to really focus on them. They occur in the tissues or cells primarily. And it really is talking about the tertiary action is not seen particularly in the cells, but we notice the damage that happens. So if we get a bunch of these lattice formations or agglutinations out in the tissues, we cause damage to cells and tissues there, and we notice the effects of the agglutination. We don't actually see the tertiary phase. So let's take and look at sensitization just in a little more detail. So the primary phase or phenomenon, that's sensitization, is quite simply the reaction of one antigen, one antibody binding. So one Fab region of an antibody binds to one epitope on an antigen. The illustration you see in this picture is showing an antigen on a red blood cell binding to the epitope of, binding to the antigen binding site of an immunoglobulin. But this could just as easily be the epitope of any kind of an antigen. It just happens to be red cells, so we're seeing one antibody binding to one antigen. We can tell this isn't, we talked about how it's not visible. The attachment is, because it's just that initial sensitization, it's the initial reaction. Remember, it's that initial bonding that's reversible. So the strength of this bond is going to be impacted by affinity and avidity, the initial attraction, and then the strength of the valency. So as a result, in the laboratory, if we're using reagents, IgM is a much more effective sensitization mechanism than IgG, because we have multivalent, we have 10 valence in order to bind and find antigens to bind to. So the issue around this is if we have too much of one reactant and not enough of another, then our sensitization phase is not effective. So if we have 10 binding sites on IgM, but we have very few antigens present, we're less likely to be able to get interactions. We don't have enough antigen binding, enough epitopes to bind with all the antigen binding sites. So sensitization isn't always kind of a slam dunk. You have to have the right quantities. Remember, sensitization, not visible in the lab. The second phase is where we count on it, and that's the lattice formation stage. So once the antibody gets sensitized onto one antibody, onto one antigen, the second phase in the lab, we start to see that cross-link of antibodies to another antigen. And I just, remember, it's the hinge is what helps us do this. It helps us play that game of Twister. The illustrations are simple, so they don't reflect it really well. We'll see a little bit better lattice formation on the next slide. So at that point, lattice formation occurs when the Fab portions of an antibody bind to two separate antigens on adjacent antigens, two separate epitopes on adjacent antigens. Antigen 1, antigen 2, epitope 1, epitope 10. I don't care what it is. But they're going to bind to an antigen on the surface, an epitope here, and it's obviously they're the same epitopes. How do we know? Because it's one molecule, right? It's one IgG or Ig, it's a one immunoglobulin. We repeat this step with more and more antibodies binding to more and more adjacent epitopes, and we get that lattice formation. Remember, if both the antibody and the antigen are soluble, we call that test reaction precipitation. Still lattice formation, but we call it precipitation. The binding of soluble antigen and soluble antibody results in an insoluble precipitant we can see. If the antigen is on large insoluble structures like red blood cells or even latex beads, bacteria, this process of latex formation is called agglutination. in lattice formation, there are going to be different things that make this an effective and strong reaction. Remember, we talked about affinity being the sum of the interactions between antigens and antibodies. So remember, if we have multiple bindings, that's going to be stronger. This structure is going to be stronger because even if this one swings away and we lose a binding, it's going to come back and bind to something else. But we haven't lost the overall structure. If we lost this one binding site, this would still be bound to this, would be bound to this, would be bound to this, would be bound to this. We wouldn't lose the visualization of this lattice formation. But as I said, there are environmental conditions that can influence this binding. Some of the physiochemical factors that affect the reaction include things like the ionic strength, pH, temperature. The electrical charges especially between red cells, are especially important for IgG. Let's go through a couple of these. Some of the reactions. IgG loves to react in the warmth. It likes to react at between 30 and 37 degrees, whereas IgM loves a good cold temperature, like refrigerator cold, up to room temperature, so between 4 and 27 degrees Celsius. The concentration of antigens and antibodies within the solution is going to have an impact. And when we talked about the electrical charges between red cells, I'm trying to remember. Nope, it's not here. We're going to talk about this again later, but imagine these are red blood cells. Red blood cells on their surface actually carry a slight negative charge that wants to push them away from each other. We have to be very careful in our test methodology that we overcome that. So sometimes we'll use a protein that can diminish the electrical charge a little, will allow these red cells to come a little closer together, or we have to use some IgG molecules, IgM. IgG has a short, kind of a wingspan, how far it can reach to grab an epitope between two different red cells. IgM is a big monster of an immunoglobulin, so it's a great reaction for red cells that don't want to stick together. They don't want to come together. So we need to make sure that we monitor that when we're developing test methods. We'll talk about that a little bit more. So those are the formations of the phases of antibody-antigen reactions. Remember, sensitization first, one antigen, one antibody, then lattice formation. Two epitopes on one antibody, two epitopes on adjoining cells get combined with the antigen binding site of one antibody. So now that we know the concepts of the stages of antigen-antibody binding, let's look at how we use this in the lab. The first test methodology that we're going to look at are called precipitation reactions. This involves combining soluble antigen with soluble antibody to produce those insoluble complexes. In order for precipitation reactions to yield visible complexes, the test really requires that we have multiple binding sites, or multivalency, both multivalent antigens and multivalent antibodies. Precipitation reactions are, because again, they're soluble to begin with. We really have to get some good binding in order to be able to visualize this. We have to have generally a relatively equal concentration of antibody binding sites and antigen binding sites. And we're going to see in a minute why that is. The activity or the function of both avidity and affinity, as well as that concentration, that proportional concentration of antigen and antibody being present, is going to what gives us that optimal precipitation visualization in a lab test. And The optimum precipitation occurs in what we call the zone of equivalence. Sounds like it's some kind of a crazy thing, but it's really quite straightforward. And what this is saying that because we have multivalent antigens and multivalent antibodies, we have to have them in relatively equal concentration. If we have too much antibody or too little antibody, then the reactions don't take place the way they need to. So let's look at the illustration and see. In the zone of equivalence, the precipitation curve, we break the precipitation curve down into three distinct areas. The first is called the prozone, and that's where we have antibody in excess, antibody excess. And you can see here we have got, very few epitopes on an antigen, but many valent antibodies here. So are we ever going to get to the point that we get that? Now this is still, is this visible or not visible, this sensitization? It's not, right? We have to get to the point that we can have that cross-linking, that lattice formation. But if I bind off one more antibody to this and one more antibody to this, I have no way to cross-link. All my antigen binding sites are bound off. All my epitopes are bound off. There's no way ever to get cross-linking. This test reaction will never be visible in the lab. So if we have excess antibody, we call that the prozone. In the post zone, we have too much antigen. So again, the concentration between antibody and antigen are not equivalent. In fact, this one was an example where we have too much antigen. So maybe lots of red cells and not enough immunoglobulin. In this case, yeah, sure, we're going to bind off the antigen binding sites on all these antibodies, and guess what happens? We never get a point that we can cross-link and see that visualized agglutination or precipitation. So the post zone is a zone where we have excess antigen, excess antibody in the prozone, excess antigen in the post zone. Did I just say post zone? I hope I did. The post zone is excess antigen. But there's a sweet spot right in the middle where we have a zone of equivalence, where roughly the antigen binding capacity is equivalent to the amount of antigen binding capacity. And this is where we start to get those lattice formations. We're able to bind one immunoglobulin to epitopes on adjacent antigens. So, for example, different cells. Then they bind off between multiple ones. This one, for example, could come undone and combine to an antigen binding site here or an epitope here, and get even larger complex. So that's our sweet spot when it's basically equivalent. So I'm not going to spend too much time here, but the prozone is that antibody excess. And we're not able to form cross linkages. This we're going to see false negative reactions occur. Because we're not going to see that cross linking. We're not going to see agglutination or precipitation. We're actually talking about precipitation here. We're not going to be able to see that precipitation occur, and it's going to look false negative to it. Doesn't mean that there wasn't actually antibody there or antigen there. There is. We just can't get to a good visualization on it because we have too much antibody in the picture. The post zone, too much antigen. Small aggregates get surrounded by all the extra antigen, and no lattice formation is again formed. This also gives us false negative results. We sometimes see this very early in the production of antibody after an initial challenge by an antibody or by a pathogen. And so we see that in some of our tests. If someone has a negative result and the doctor really thinks that they have that disease. Maybe it's, strep, it's a strep reaction or something. If they repeat the test a week or so later and the antibodies had time to form, we may end up getting a positive test. Not because the antigen wasn't there before, we just had too much antigen and not enough antibody being formed yet. So if the test is negative, sometimes if you repeat it a week later, you can develop more antibody and be able to see a positive test. If a week later the test is still negative, it's unlikely the patient has developed any antibody to the antigen. And again, this is just another illustration because some people like to see things differently, and just shows you how the antigen excess or the antibody excess inhibits the ability to visualize the test with through lattice formation. No lattice formation, no lattice formation, lattice formation. This looks like this is too weak to be lattice formation. It's a couple little things stuck together. So we're going to look at a number of precipitation reactions today. We're going to look at turbidimetric, nephelometric, radial immunodiffusion, Octolani, immunoelectrophoresis, and immunofixation electrophoresis. I'm going to break this up right now, and we will go into each one of those in detail in just a few minutes, but I want to break the lecture into two pieces. Thanks, so I'm going to stop this now. Oops, there we go.